Hey everyone, so today we're going to be talking about polynomial and rational inequalities. First up, let's talk about the definition of a polynomial inequality. A polynomial inequality is any inequality that can be put into one of the following forms: f of x less than 0, f of x greater than 0, f of x less than or equal to 0, f of x greater than or equal to 0, where f is a polynomial function. In short, a polynomial inequality is an inequality comparing a polynomial function in 0, whether that it is less than, it is greater than, less than or equal to, or greater than or equal to it. So here's an example of a polynomial inequality. X squared greater than or equal to 0. X squared is a very basic polynomial, and we are talking about it being greater than or equal to 0. So now that we've introduced a polynomial inequality, let's move on to solving polynomial inequalities. Step 1. Express the inequality in the form f of x is less than 0 or f of x is greater than 0, where f is a polynomial function. The reason we have this step is because your problem may not start off in this form. It might take the form of f of x is less than 5 or greater than negative 6. And then we need to rewrite this expression to get it in this form. Now notice that we have just listed less than or greater than. This also applies to less than or equal to and greater than or equal to. Solve f of x is equal to 0. So what we need to do is set this function equal to 0 and then find the values of x that make this true. We will call these real solutions boundary points. So now we have our boundary points in hand. What we want to do now is locate these boundary points on a number line. So we are dividing a number line into different intervals where these boundary points serve as, well, the boundary for these intervals. So now that we have these intervals, we want to pull a test value from each interval. In other words, just some number from the interval in question, and then evaluate f at that number. So when you're choosing a test value, all it has to do is be a number from that interval. But what I suggest doing is, when trying to decide what test value to use, find a value in the interval that is easy to evaluate with the function. So say you have an interval from 0 to 2. Don't evaluate your function at 0.317. That'll just cause an unnecessary headache. In that case, just choose the number 1 or something simple like that. Now, once we evaluate f at that number, one of two things can happen. If the value of f is positive, then f of x is greater than 0 for all numbers in that interval. That's why it's a test value. Think of it as a representative of the interval. We have already found the values that make f equal to 0. So now we're interested in finding the values that make it positive or negative. And to do this, from the interval, we need to pull out this test value and then test it. Does it make f positive or does it make f negative? And what this will do is actually be the actual value for all the numbers in that interval. And we can do the same thing if f is negative. If the value of f is negative at that test value, then f of x is less than 0 for all the numbers in that interval. Step 5. Write the solution set, selecting the interval or intervals that satisfy the given inequality. So the solution set is merely the collection of all the values of x that make the initial inequality true. So that's really what we're trying to do when we're solving a polynomial inequality. We are trying to find all the values of x that make the inequality true. These steps are all fine and dandy. Now let's see an example. Solve and graph the solution set of x squared plus 11 greater than 20. Now, step 1. Express the inequality in the form of f of x is greater than 0 or f of x is less than 0. So we have x squared plus 11 is greater than 20. This is not in the form that we need yet. What we need is just the polynomial on one side and a 0 on the other. So what we need to do is subtract 20 from both sides. And then we have x squared minus 9 is greater than 0. Now we're in the form we want. We have a polynomial, in this case x squared minus 9 greater than 0. This is the form we can do something with. Step 2, we need to solve the equation f of x is equal to 0. Remember, our f of x is now x squared minus 9. So we need to set this equal to 0 and then solve. So to do that, let's factor this in to x minus 3 and x plus 3 equal to 0. And this tells us that to make f of x equal to 0, x must equal 3 or f must equal negative 3. So in short, these are our boundary points. X is equal to negative 3 and x is equal to 3. Step 3, we need to put them on these boundary points on a number line. We want to see where they are and how they break up the number line in terms of intervals. So we have our point x is equal to negative 3, our point x is equal to 3, and now we need a number line. Now let's put these on here. Negative 3 goes there, and 3 goes there. And now we can kind of see the three intervals that we're working with. Negative infinity to negative 3, negative 3 to 3, and 3 to infinity. Okay? Notice that we're not including any of these boundary points here. That's because the inequality has a strict greater than. It's not a greater than or equal to, it's a strict greater than. So now we need to come up with this table. We need to put our intervals, we need to pull them down, and we're going to examine each one individually. Now, from each interval, we need to pull out a test value. I have chosen negative 4, 0, and 4 because they're nice whole numbers that are easy to calculate with that lie completely in the interval. Now we need to evaluate them. So evaluate f of negative 4 is equal to negative 4 squared minus 9, which is equal to 5, which is greater than 0. F of 0 is equal to 0 minus 9, which is equal to negative 9. F of 4, which is equal to 16 minus 9, which is equal to 5. From this, we can conclude that on the interval negative infinity to negative 3, f is positive. On the interval negative 3 to 3, f is negative. And on the interval 3 to infinity, f is once again positive. Step 4. Step 5. Write the solution set, selecting the intervals that satisfy the given inequality, that is, the intervals that satisfy this. From step 4, the previous step, it follows that the solution set is negative infinity, comma, negative 3, union 3 to infinity. What this means is if we pull any x value from these intervals and we plug it into this inequality will be true. Now let's graph it. These are the solution sets. First up, negative infinity to negative 3, but not including negative 3. So if you look closely at the graph, that looks like it's a parenthesis right there. It means open interval. We're not including negative 3. And then we need the other interval, 3 to infinity. Once again, notice the parenthesis. That means it's everything but not including the endpoint. Now, we spent a lot of time talking about polynomial inequalities. Let's move on to rational inequalities. Now, a rational inequality is any inequality that can be put into one of the following forms. F of x is less than 0, f of x is greater than 0, f of x is less than or equal to 0, f of x is greater than or equal to 0, where f is a rational function. So this is the exact kind of setup that we had just had with the polynomial inequalities, except this time we're using rational functions rather than polynomial functions. Here's an example of a rational inequality. 2x plus 1 over x greater than or equal to 0. Now that we've kind of seen an example of what a rational inequality looks like, let's see how we can go about solving a rational inequality. So our task is to solve and graph the solution set for 2x over x plus 1 is greater than or equal to 1. Now, the steps are going to be just the exact same that we just did for solving the polynomial inequalities. The techniques and the strategies can be applied for both kinds of problems. So step one, we need to express the inequality so that one side is 0 and the other side is a single quotient. And what I mean by single quotient is because we need it to be a rational function. If we have two different fractions or something in there, then it's not a rational function anymore, it's two rational functions. So we need one side to be a rational function and the other side to be 0. So for this one, we have 2x over x plus 1 is greater than or equal to 1. Subtract 1 to both sides, which results in 2x over x plus 1 minus 1 being greater than or equal to 0. But 1 is not a fraction. So what we need to do is give it a common denominator with the other fraction. So we can rewrite 1 to be x plus 1 over x plus 1. Now we can combine the two fractions and create one single fraction. Then we have 2x minus quantity x plus 1 divided by x plus 1 is greater than or equal to 0. Now this is what we want. This is the form this is our final form, so to speak. This is the form that we know how to work with. This is the form that we have developed techniques to deal with. So our final result is this rational function. X minus 1 over x plus 1 is greater than or equal to 0. So now we have our setup. Now let's go about solving it. Based on the algebra we just did, we have shown that x minus 1 over x plus 1 is greater than or equal to 0 is equivalent to the problem of 2x divided by x plus 1 being greater than or equal to 1. And it is in the form f of x greater than or equal to 0. This is important. We need these two inequalities to be equivalent. If they're not equivalent, then it doesn't make much sense to be solving this new inequality that we have come up with. Step 2. Set the numerator and the denominator of f equal to 0. We want to do this because this will tell us where our boundary points are. So set the numerator equal to 0. We have x minus 1 is equal to 0. So x must equal to 1. So x is equal to 1 is our first boundary point. But now we got to check the denominator. So we set x plus 1 is equal to 0. And then we get x is equal to negative 1. So these are our two boundary points. X is equal to 1 and x is equal to negative 1. Next step, we need to put these boundary points on a number line. So if we recall, our boundary points are negative 1 and 1. So let's put this on a number line. So negative 1 goes there and 1 goes there. Cool. Now we have found them on the number line. Now we need to identify the intervals. The intervals in question are negative infinity to negative 1, negative 1 to 1, and 1 to infinity. Now we need to pull a test value out from each one of these and evaluate f at that test value. So let's pull our intervals down here, shall we? And now let's pull a test value out from each interval. Let's pull out negative 4, 0, and 4, just like we did on that last example. Now let's evaluate f at these points. F of negative 4 is equal to 5/3, f of 0 is equal to negative 1, and f of 4 is equal to 3/5. From this, we can conclude on the interval negative infinity to negative 1, f is positive. On the interval negative 1 to 1, f is negative. And from 1 to infinity, f is positive. Now, we've been tasked with writing the solution set, selecting the intervals that satisfy the given inequality. That is, the intervals that satisfy this. From step 4, it follows that the solution set is equal negative infinity comma negative 1 union 1 to infinity. Now notice here, we have a bracket on this interval 1 to infinity. That's because if you plug 1 in to our inequality, you get 0 over 2, which is equal to 0, which satisfies our inequality. When you have a less than or equal to, you need to check the endpoints to see if they satisfy the inequality or not. If we plug in negative 1, then we have a 0 in the denominator, which we can't do. So that's why negative 1 is not included in this solution set. So now let's graph it. We have our number line. We have our first interval, negative infinity to negative 1. Notice the use of the parenthesis at negative 1. That means the solution set contains all of the negative numbers less than negative 1, but not including negative 1. And now we have this interval, 1 to infinity. But notice here we have a bracket there because that means all the numbers greater than or equal to 1 satisfy the given inequality. So this is the graph of our solution set to the inequality. Now it's kind of fun that we've developed these techniques for solving these inequalities, but you might be asking yourself, okay, this is all cool and everything, but what's the point? Well, here we're going to show you an application problem to show how using our knowledge for solving these inequalities can come in handy. Consider this problem. An object is propelled straight up from ground level with an initial velocity of 80 feet per second. Its height at time t is modeled by the function s of t is equal to negative 16t squared plus 80t, where the height s of t is measured in feet and the time t is measured in seconds. So this is our problem. An object is being thrown up straight up from ground level at a very fast initial velocity. And we have a function that models the height of the object at a given time t. So the question is this: in which time interval will the object be more than 64 feet above the ground? So what this is asking is, it wants to know what time interval will the object be more than 64 feet above the ground. In other words, what time values, at what time is this object going to be more than 64 feet above the ground? What we need to do is solve this inequality. Negative 16t squared plus 80t is greater than 64. So, how can we go about doing this? By using the stuff we have been using this entire lecture. First up, step 1. We need to get this into a form we can work with. Right now, it's not quite there. We need a polynomial on one side and 0 on the other. To do this, subtract 64 from both sides, just like this. So we are resulting with a polynomial on the left and 0 on the right. Now, we want to solve for the values of t that make this polynomial equal to 0. We want to go find our boundary points. So set f of t equal negative 16t squared plus 80t minus 64. And then we need to set it equal to 0. Okay. Just this first line here is just reiterating the inequality we wish to solve. We need to set it equal to 0 and recognize that negative 16 is common to each term in the polynomial. So we can go ahead and pull that out and just divide that through. Or we can just leave it there. And so we have negative 16 times t minus 1 times t minus 4 is equal to 0. Now by looking at this, we notice that there are two values of t that make this equal to 0. T minus 1 equal to 0 implies t is equal to 1, and t minus 4 is equal to 0 implies t is equal to 4. So these are the two t values that make our polynomial equal to 0. In other words, we have found our boundary values. They are x is equal to 1 and x is equal to 4. So what these boundary points are, they give us three intervals. The interval 0 to 1, 1 to 4, and 4 to infinity. Now notice we do not have an interval from negative infinity to 1. That is because we're talking about time in terms of seconds. It doesn't make sense to talk about what happened 10 seconds ago. We can't go into the past right now. We can't do that. Time starts at 0. So that's how we end up with these three intervals. Now, if you pull out a value from each one of these intervals and evaluate the function at these 3 points, we find that the inequality is true for the interval 0, 1 to 4. What this means is our initial inequality is satisfied for all the time values in the interval 1 to 4. So this means the object will be more than 64 feet above the ground between 1 and 4 seconds, excluding t is equal to 1 and t is equal to 4. So that's all I have for you today on polynomial and rational inequalities.